Hello, in this screencast, let's take a look at the chemistry of gas mixtures, or what is described as Dalton's law of partial pressures. Dalton's law of partial pressures states in a nutshell that if you have a mixture of gases all sealed up in the same container, each of the individual gases will exert their own individual pressure. Each of these individual pressures is called the partial pressure. So Dalton's law would state that the partial pressures of all of the gases in a mixture of gases add up to give you the total pressure of the entire mixture in the same container. So, if we take a look at this mixture over here on the left, each of the circles stands for 1 mole. So, the single solitary orange circle stands for 1 mole of gas A. In a similar way, we have 5 moles of gas B and 4 moles of gas C for a total of 10 moles of gas in the container. If each of these circles stands for 20 atm, this means that we have 100 atm of gas B and 80 atm of gas C. So each of these pressures would be the partial pressures of that particular gas. So to figure out the total pressure of the entire gas mixture, you would add up the partial pressures. So it would be 20 plus 100 plus 80 to give you a total pressure of 200 atm. So it's actually a very simple law on the surface. However, know that we have to make some assumptions in order for this to be that simple. And the assumption is that kinetic molecular theory, or KMT, will hold, and all the gases in the tank are acting ideally, meaning that there are no chemical reactions that occur during collisions, since all collisions are elastic. This is just for us to simplify our picture of what's going on in the tank. Because if we don't, and if we assume that chemical reactions do occur, let's say that the reaction happens to be A plus B collide and to give you gas C. If chemical reactions did indeed occur, that means the total number of moles of gas A would decrease as the reaction proceeded because A would get used up. In the same way, the moles of gas B would get used up, and the total number of moles of gas C would be constantly increasing, or would be increasing until either A or B ran out. However, there's no way to tell, like at a glance, just how many moles of A and how many moles of B that you have in the tank at any given moment. You also can't really tell the number of moles of gas C, and just know that that picture would be constantly changing as more of A and B get used up and as more moles of gas C accumulate inside of the tank. All of those numbers of moles changing is going to constantly change the pressures. So just to make things simple, we just assume that none of this goes on, that there are no chemical reactions, and that all gases are acting ideally. It's just easier for us as far as calculations go, because if chemical reactions were indeed occurring, then we need to worry about gas stoichiometry on top of everything else. That's for next class, but for today, let's keep things simple and assume that KMT will hold. So let's flip the script and let's look at the influence of the number of moles on pressure, because it does absolutely have to do with the total pressure in the tank. So let's say that we know we have 1 mole of gas A, 5 moles of gas B, 4 moles of gas C. In order for us to do some further calculations with partial pressure, we need to understand a concept called mole fraction. Mole fraction is, simply put, the number of moles of that one gas you are studying divided by the total number of moles in the tank, including that gas that you are studying. Hence the term mole fraction. It is a ratio of the mole of your gas of interest divided by the total. And if to you it sounds kind of sort of like percentage, you're right, except that we are not multiplying by 100%. So mole fraction has the symbol X. So X sub A stands for the mole fraction of gas A. We know in this case that there is only 1 mole of gas in the tank. So to solve for the mole fraction, we're going to divide 1 mole of gas A by the total number of moles in the tank, which is 10. Therefore, X sub A is 1 over 10. In a similar way, you can solve for the mole fraction of gas B, which is 5 over 10, or 1/2. And the mole fraction of gas C would be 4 over 10, which is really 2 over 5. Alternatively, since there are only three types of gases in the tank, you could solve for x sub A and x sub B, add up those two x values, and then subtract them from 1 because 1 is really 100%, just not as a percentage. So now let's take a look at how we can use mole fraction in calculations for Dalton's law. So let's say we know in another problem that the total pressure is 200 atm, but we don't know the partial pressures of each individual gas. We can use the mole fraction. So partial pressure of gas A is the total pressure multiplied by the mole fraction of gas A. So therefore, partial pressure of gas A is equal to 200 atm multiplied by the mole fraction of gas A, which we previously solved as 1 over 10. 1 over 10 is a ratio, so we're not going to use that for significant figures rounding purposes. So we're going to use the 200 ATM as our indicator for the sig figs. 200 times 1 over 10 is 20.0 ATM. In a similar way, you can solve for the partial pressure of gas B as well as for gas C. Now let's take a look at how to use mole fraction, among other things, to solve for Dalton's law problems that are a little bit more difficult. So you're given that we have a heliox or a helium-oxygen mixture. There are 15 liters of it, so that's our volume. We are told the mass of two gases in the tank. I just realized that's not carbon dioxide, it should be helium and oxygen. So we're going to solve for the number of moles of each of these individual gases first, after we go over the rest of the data here. 25 degrees Celsius is going to be our temperature, but we're going to add 273 to it. This is going to be 270, 298, sorry, not 270 anything, 298 K. We're going to calculate the partial pressure of each gas in ATM and total pressure of the gas in the mixture, also in ATM. So we're going to solve for the number of moles of helium. So this is going to be 20.0 grams, and we're going to divide by the molar mass of helium, 4.003 grams. So we have about 5 moles of helium in the tank. So yeah, 4.996. Notice I'm not really caring about sig figs right now because we are after pressure. That's going to entail some more calculations, so I will deal with significant figures at the end of the problem, not right now. In a similar way, I'm going to solve for the number of moles of oxygen gas. So we have 20.0 grams of oxygen, divide by the molar mass of oxygen, which is 31.998. Recall that oxygen is diatomic. So the number of moles of oxygen in the tank is but 0.62504. So in this way, you can get the number of moles of each of the gases. Since there are no chemical reactions occurring, the total number of moles in the tank is just going to be 4.996 plus 0.62504. And there are no other gases, so that should make things easy on that front. So you add these up and you'll get the total number of moles as 5.62 104 moles. So we have moles, we have volume, we have the temperature. We could solve for pressure. Just know that in this case, you'd be solving for total pressure if you've added up the number of individual moles of each gas. There's nothing that says you have to do the partial pressure of each gas first, after all. So total pressure, or P sub T, is going to be nRT divided by V. So that's the ideal gas law, except that N is going to be N sub T. It's going to be the total number of moles. So we're going to put 5.62104 moles. We're looking for ATM, so let's use 0.0821 for our R value. And multiply 298K by that. And then divide by the total volume, which is 15.0 liters. Before we go on to solve for the total pressure, just know that you can absolutely solve for the partial pressure of each gas, which we'll do in a minute. Just know that there's no such thing as partial volume. I see kids making that mistake a lot. The volume of the mixture is 15 liters, but so is the volume of the helium on its own and the volume of the oxygen on its own. So each of those individual volumes is still 15 liters. That's because gases fill their containers. However, that does not mean the individual pressures of each of the components in the tank is the same as the total pressure, because it's not. It has to do with the number of moles. So when we solve for the total pressure in ATM, we will get, my calculator says 9.1682 ATM. Let's go ahead and figure out our sig figs. All of these numbers have three significant figures, so we're going to add, just round this to 3 sig figs. So we're going to put 9.17 ATM for our total pressure. So that takes care of that part of the problem. Now to do the partial pressure, we do have the individual numbers of moles after all, so we can go ahead and solve for, say, the partial pressure of helium, which is going to be 9.1682 ATM times, we know the number of moles of helium was 4.996, and the total number of moles was 5.62104. So this part here is the mole fraction of He. So solve and get 8.15 ATM. I will round this to 3 sig figs now. So there's our helium partial pressure. There's only one other gas in the tank, so you could just subtract to find the partial pressure of oxygen. So that would be 9.17 ATM, which is the total, minus the partial pressure of the helium, and therefore the partial pressure of just the oxygen in the tank would be 1.02 ATM. So it's kind of long in the sense that you have to solve for the number of moles first, but it's completely doable. Just know that the total number of moles of gas in the tank can be used to solve for total pressure first, and then you could solve for partial pressure after that. Let's take a look at another way in which you can solve the same problem. So in this other way of solving the same problem, no, you still have to find the number of moles of each individual gas. So I have gone ahead and rewritten all of that stuff from the previous slide. But here's where we diverge from the first method. You can solve for the partial pressure of each gas right now. Just know that you would be doing this twice, right? You'd be doing this once for the helium and then once for the oxygen. Once you have those two partial pressures, you can just add those two up to get the total pressure of the gas in the mixture. So to solve for the partial pressure of helium right away, this is going to be the number of moles of just helium times R times T divided by V. Now, whoops, typo there. Note that, again, there's no such thing as partial volume. The volume of helium is still 15 liters. So the number of moles of helium, 4.996 moles, times 0.0821 liters times atmospheres over mole K times 298 K, all over a total volume of 15 liters, which is the same as the volume of just the helium. Solve and you get 8.148. This is one of our answers, so we're going to round this to 3 significant figures, so 8.15 ATMs. So that's one of our answers. We're going to do the same kind of thing, but for oxygen gas. So PO2, we're going to multiply N of O2 times R times T divided by the volume of the oxygen gas, which is again 15 liters. So 0.62504 moles times 0.0821 liters atmospheres over mole K times 298 K. Divide all of that by 15 liters, and you get 1.02 ATM Again, rounded to three significant figures. So to get the total pressure, we're just going to add up the individual partial pressures together. So 8.15 plus 1.02 gives you 9.17 atm, which would be all of the answers that we got in the previous sort of problem, or the previous sort of strategy. So use whichever one of the two strategies works best for your brain. Now, where this